Hey everyone, today we're diving into something really cool, a powerful statistical tool that's basically an invisible detective. It's all about uncovering hidden secrets from clues that are hiding in plain sight. Let's get into it.
So, to get our heads around this, let's start with a little puzzle. Imagine you've got a friend living in a city halfway across the world. How on earth could you figure out their daily weather, whether it's sunny or rainy, without ever getting a weather report or even talking to them about it? It sounds pretty much impossible, right? Well, that's exactly the kind of mystery we're going to solve today.
And we're going to do it with a simple story about two friends, Neha and Raju. This little mystery is the perfect way to understand the core logic behind our invisible detective.
Okay, so here's the setup. Every single day, Neha gets an email from Raju, and this email has just one piece of information, one single observation, what Raju did that day. He either walked his dog or he stayed inside and read a book. That's it. This is our data. It's the only clue Neha has to work with.
But here's the twist. Raju's choice isn't random at all. It's actually influenced by something Neha cannot see, the weather in Singapore. The weather is the secret, the hidden piece of the puzzle that's driving all the clues Neha is getting.
So what we really have here are two different layers to our mystery. There's the hidden layer, the states of the weather, and then there's the observable layer, the emissions of Raju's activities. Neha's big challenge is to use what she can see to figure out what she can't.
And believe it or not, this whole setup, this entire detective problem, actually has a formal name. It's called a Hidden Markov Model, or HMM for short. It's a statistical tool designed for exactly this kind of thing, using a sequence of visible events to figure out the sequence of hidden states that cause them.
So, how does an HMM actually make its predictions? I mean, how can Neha possibly make an educated guess about the weather? Well, she needs a model, and that model is built on two really fundamental sets of rules, or more accurately, probabilities.
Okay, rule number one is all about how the hidden state changes over time. We call this a transition probability. In our story, it basically just means that weather is kind of predictable. If it's sunny today, there's a really high chance it's going to be sunny again tomorrow. This is the first key piece of the puzzle. The system has a memory. Today's weather influences tomorrow's.
The second rule is what connects the hidden state to the clues we can actually see. This is the emission probability. It tells us how likely an observation is given what's happening in the hidden layer. So if it's sunny, there's a super high chance that Raju emits the activity walks dog. And this is the other crucial piece. It's the link between the hidden and the seen. Without this, Neha's clues would be totally meaningless.
So, okay, we figured out a little weather puzzle. But what's the big deal, right? Well, this is where it gets really mind-blowing, because this exact same detective logic is used to unlock one of the most profound mysteries of all, the code that's hidden inside our own DNA.
Think about it. The human genome is billions of letters long. And it's not just some random jumble of A's, C's, G's, and T's. It's organized into different functional regions. But here's the problem. Those regions aren't labeled. They're hidden. So how in the world do scientists find them?
And this is the perfect analogy. We literally just swap out the pieces of our puzzle. The hidden states are no longer sunny or rainy. They're different types of DNA regions, maybe an AT-rich region or a GC-rich one. And the observations? They're no longer walk or read. They are the four nucleotide bases, A, C, G, and T. The logic is 100% identical. Just like Neha uses activities to guess the weather, scientists use a sequence of DNA bases to map the hidden functional regions.
And yup, you guessed it. Just like the weather, our DNA has transition probabilities. A DNA sequence is probably going to stay in a GC-rich region for a while before it switches over to an AT-rich one. These numbers tell the model that once it's in a certain type of region, it's likely to stay there for a bit, which reflects how genes are often clustered together. The model is actually capturing the underlying structure.
And of course, we have our emission probabilities too. An AT-rich region is, well, by definition, way more likely to emit the letters A or T. This is what lets the model see the signature of a hidden region in the DNA letters themselves. It leaves behind this clear statistical fingerprint for the model to follow.
So this is the crucial part. We have a model, we've got all these probabilities, but just having the rules isn't enough. How do we actually apply them to a massive DNA sequence to find the most likely map of hidden regions? For that, we need the power tools, the algorithms that do the heavy lifting.
This is the million-dollar question for a bioinformatician, isn't it? You're given this huge string of letters. What is the single most probable path of hidden states, the most likely story that could have created it?
And the tool for that job is the Viterbi algorithm. You can think of it like a master detective. It sifts through all the countless, mind-bogglingly numerous possible paths of hidden states and efficiently calculates the one single path that has the highest probability of being right. It reveals the most likely story.
Now, you might be thinking, okay, this is all great, but wait a minute. Where did we get those probability numbers for the tables in the first place? For the weather, sure, Neha might have some past data to go on. But for DNA, where do you even start? We have to train the model.
And that's where another brilliant tool comes in, the expectation maximization algorithm. It's this really clever repeating process. You start with just a random guess for the probabilities. Then, in the expectation step, you use those guesses to map out the hidden states. In the maximization step, you look at that map and update your probabilities to better fit what you're seeing. And you just repeat this loop, guess, check, refine, over and over, until the numbers stop changing and you've found the best possible parameters for your model.
So now that we have the full toolkit, the model itself, the decoder algorithm, and the trainer, we can really start to appreciate just how massive the impact of hidden Markov models has been across science, way beyond just finding GC-rich regions in DNA.
I mean, this same fundamental logic can be used to predict the 3D structure of proteins, to find critical sites in genes where splicing happens, or even to model how a disease might progress based on clinical data over time. And get this, it's even used in technologies we use every single day, like speech recognition, where the hidden states are the words you're saying and the observations are the sound waves.
You know, there's a quote from our source material that just nails it. It says, HMMs are for answering questions like, is there a particular pattern here? Does this sequence belong to a certain family? At their core, they are pattern finders. They take what you can see and ask deep questions about the hidden structure.
And that is why this all matters. We're not just talking about some niche academic tool. Hidden Markov models are a true workhorse of modern science, enabling literally thousands of discoveries that have fundamentally changed how we understand genetics, medicine, and so much more.
Which leaves us with one final and, I think, fascinating question. The world is just full of observable data that's being driven by hidden processes. Everything from stock market prices to animal behavior to how ideas spread online. What other invisible patterns are out there, right in front of us, just waiting for the right model to finally make them visible?